right, good morning, everybody. Good afternoon. Um, Welcome to our last week of Math 3000. Um, don't know if there are crying emojis that you guys could use, but I'm sure if there were, you guys would be expressing your thoughts. Admiral Akbar is holding back the tears, I can see. So the plan today is to just kind of wrap up the material for this semester. So just to kind of wrap up what we've been talking about with cardinalities. And so this will be the end of the material that you'll have on your last exam. So the exam will cover this stuff, although you don't have any uncountable stuff on your homework assignment, which is due this week. This material will be on the exam. Just want to be clear about that. So I did electronically return your homeworks. So you should be able to see the comments on that assignment. And I'll just say, things look really good. The grades are looking really good on them. Sometimes I provide a lot of comments, even if I don't deduct points. So please do kind of pay attention to some of those things. I'm not being nitpicky. I just, I'm a perfectionist. I don't know. I don't think there's any such thing as perfection. So there's always some way to try and improve things. So that's my job, is to just give you that feedback. I'm not trying to be overly critical. I think your work is great, generally speaking. I'll just say, for a couple of people, I don't know if it's like the end of this semester, but your proofs started to drift away from using words and sentences and drifting back towards just using notation and writing out equations and not explaining what you're doing. So I don't know, I kind of feel like my job is a trainer, and it's like you're doing push-ups, you're not going all the way down anymore. You got to go all the way down, finish off strong, and just keep on writing things out. So I left comments like that on people's assignments. Maybe it's just late in the semester, but please watch out for that on the last homework assignment as well as on the exam. So kind of some of the things that even people that are writing out really nice proofs can pay attention to are things like labeling parts of your proof and indicating what type of proof you're doing. So those are things that I will be looking for on the exam. So if you do that, you'll certainly be earning some credit, even if you make some mistakes in those parts. So before we get going today, also, I wanted to say thank you all for the good response rate on the FCQs. I really appreciate that. If you haven't done them yet, we've got close to 80%. You have until midnight tonight to get those in. Okay, so otherwise, any questions about things before we get started today? Okay, so we'll be working on worksheet 23 today. And so I want to just kind of start with something that we talked about last time, and then we can see an alternative way that we might be able to do this. So last time we were proving things are countably infinite. And so the map that we set up when we did this, and these are not unique, was we said, let's first map to 0. So we'll take the first natural number 1 and map that to 0. And then we need to map to positive and negative integers. So we'll use all of the even numbers to map to the positive things. We'll use the odd natural numbers to map to the negative integers. And we kind of wrote that out. Again, there's nothing special. I could have mapped 1 to -2 and then tweaked things around that way. But if I do it this way, then what we kind of saw working our way towards finding an equation is then we just kind of listed out what we were doing. So 1 is going to 0, 2 goes to 1, and so on. And maybe this helps recognize a pattern, and then we can find formulas for what's happening with the even numbers and what's happening with the odd numbers separately. And again, this is what we did last time on Wednesday, and we came up with the following formula for that. Any questions about that? So what we didn't do last time, and I'm not going to go through like all of the details, but I just kind of want to illustrate what a proof of this would look like. So I'll just say some of the proofs for the injective and surjective properties that were on your last homework. This kind of goes back to writing out proofs. We're slipping away from being formal a little bit and just kind of writing out some equations and not connecting them. So when we're doing injective and surjective proofs, they should look like proofs. They should be mostly words explaining things that are going on. So if I want to prove that the integers are countably infinite, then I define a function f, and then I want to prove that this function is bijective. And I don't just say, here's my function f, reader, you check that it's bijective, right? That's not fair. The reader isn't supposed to do the work. You're supposed to do the checking for the reader. So then you would need to go through and verify to the reader, this is why it's injective, and this is why it's surjective. So some of the things that I'm looking for in your proofs, just to be clear when I'm grading, is, okay, did they label this part? And is it clear what proof technique they're doing before I start reading the proof? It's really helpful for me to see what your technique is before I start to read. I've got my cases labeled and so on. And then for the surjective proof, for this one, I did this one directly, so I don't need to indicate what proof technique was done there. But there are some details to show with these. So any questions about that? Yeah, so definitely, keep on practicing these injective and surjective proofs. If you want to prove something is countably infinite by constructing a bijection, you're going to have to keep on practicing some of those. Okay, so let's talk about another method that we can do this. So let's first kind of prove this result, and then we can see how we can apply it to the previous example to get an alternate way of proving that. So in this case, right, anytime we're reading a claim, a theorem that has an if and only if, right, this means it's biconditional, and that means we need to do two proofs. Okay, and again, when we're doing these biconditional, it's nice to just label the parts of this proof, which are not injective, surjective, but forward and reverse direction. So for the forward direction, we're gonna assume A is countably infinite, and then prove that we can arrange the elements of A in a list, an infinite list like this. So we're gonna do this directly, so I'm not gonna need to indicate any other proof technique. So we're gonna start by assuming the hypothesis, in this case, in the forward direction, A is countably infinite. And so if A is countably infinite, our definition of this means that therefore there's a bijection from the natural numbers into A. And we don't need justification for that. That follows directly from A being countably infinite. And again, what we're hoping to show here is that we can arrange the elements of A in an infinite list. So this means that we can therefore list the elements of A we'll say the first element in my list of elements of set A is going to be the image of 1. Right? And we can just kind of list them out like this. And then we just need to prove that this is going to be able to list all of them. And that's going to follow from the properties that F is a bijection. Okay, so since F is surjective, that means every single element in A is going to be in our list since there's some natural number which is mapped to it. And since it's injective, we know we're not double listing things. So each element of A appears exactly once in the list. So that proves the forward direction that if it's countably infinite, then we've got a list that we can create. Any questions? Okay. Then we're not done, right? We need, because this is biconditional, we then need to prove the implication in the other direction. So now we're going to suppose the elements of A can be listed, arranged in a list. And what we need to do is show that it's countably infinite. We need to show that there's a bijection from the natural numbers into set A. So how do you think we want to define this function?
Is it just ace of n?
Yeah, let's just kind of use the same function essentially that we had up here, right? So here we started with a function. From that function, we can generate a list. And we can do this, it's almost like the inverse, right? Now we are starting with this list. So I'm just going to define f of n to be whatever the nth element is in that list. And I'll leave this for you as an exercise to do at home, since I want to kind of focus on the issue of cardinality, not as much the injective, surjective stuff that you had on the last homework. But I just want to be clear that just giving the function isn't the proof. We also need to prove that it's a bijection. But hopefully it makes sense that we've got this list. So the list includes all elements of A. That's going to make it surjective, and we're listing each thing once. So that's going to make it injective. Okay. So to come back to this example over here, using this idea, we could set up a list as follows. We could say A sub 1 is 0, A sub 2 is 1, A sub 3 is -1, A sub 4 is 2, A sub 5 is -2, and so on. And we can start to list all of the integers. So this theorem is really powerful in that if we can just create a list, then we don't need to do injective, surjective proofs. We can just use the result of theorem 1 that we've now proven together. This one over here is the list for Z. So this could be the proof for Z. We would just want to convince readers that this is going to be able to list all of the integers. We did one with Q rationals last time. So if I want to prove that Q is countably infinite, last time, this is what we did, basically. We didn't really have a nice, clean formula for doing this. We just said we're going to start here, and here's a 1. And then here's a 2, here's a 3, here's a 4, here's a 5, here's a 6. And anytime we happen to hit one that we've already counted, we skip it. But this gives us a way of showing that we could snake through all of, these are actually positive and negative, right? We've got negative values in here too. So here's a proof for proving the integer, the rational numbers, positive and negative, are countable. Any questions so far? So what that proof would look like here, if you're going to use that, just indicate the proof technique. Usually the generic technique is to set up a bijection, so you don't need to explain that. That would be clear in your proof. If you're going to do it using this way, then just claim we're going to prove this by infinite list, and just show how you could list them. Theorem 2 is a result saying that any infinite subset of a countably infinite set is countably infinite. I think that might make some sense, probably intuitively. That's not too surprising. But let's kind of just prove this now that we have the previous theorem. So again, if it's hopeful logic-wise, you might want to restate this theorem as an implication. If we have an infinite subset of a countably infinite set, then that subset is countably infinite, right? That's what this would look like as an implication. So we're going to do this directly, so I don't need to indicate anything. We're going to suppose set A So that's our hypothesis there. And what we want to show is work our way to showing that A has to be countably infinite. And we can do this by either constructing a bijection from one set to the other, or by showing that we can list them. And based on where we've got this theorem here, since we don't actually have concrete elements in set A or set B, it's going to be hard for us to come up with a concrete map. So let's try and use the arranged in a list implication here. So since B is countably infinite, then that means we can arrange elements of set B in a list. I should say an infinite list there. So how do you think we can get a list of the elements of A based on this? So what do you think like my first element A is going to be in the list?
Probably the same thing, right? Because if it's a subset, it follows the A1, A2, A3. Is that what you're saying, or?
Yeah, so I want to show that we can list all of these elements of A in some infinite list. And then that's going to tell me that by theorem 1, A is going to be countably infinite. So I've got a list of elements for B, and I'd like to construct a way of listing elements for A. So I want to say, okay, what's going to be my first element in this list? What would be a natural choice?
Yeah, B1, right?
We tried B1, right? But it's possible that B1 is not in set A, right? Since A is an element of B, since A is a subset of B. So we start with B1 and we say, okay, if B1 is in set A, we put it over here. If it's not in set A, then we would skip it and go to the next one. And if this is not in set A, then we skip it and go to the next one. And we just proceed through the list like that. And so hopefully that you guys can see that this is going to give us a way of listing all of the elements of A out in a list. And since A is infinite, right, this is going to be an infinite list of things. So let me just describe that more clearly to the reader, how we're going to set up this list. But that's the idea. We're just going to go through the list of B, pick off the ones that are in A, ignore the ones that are not in A. So we're just going to proceed through the list of elements of B. And that would give us a list that would arrange all of the elements in A in a list. So this tells us that any infinite subset of the rational numbers, right, is going to be countable. So that would give us, any subset you can imagine of the rational numbers. Any questions about that? Okay, part of the goal for today was to kind of go through this alternate way of proving things are countable by listing them. And then I want to move on and now talk about things that we can't list, things that aren't countable. come over here. So a couple of things just to summarize. If we want to prove that two things have the same cardinality, whether that's finite or countably infinite, then we want to show that there's a bijection from A to B. And let me just say a special case of this is if we want to show A is countably infinite, then what we need to show is there's a bijection from N into A. Okay, so we pick our domain as N. But we can compare two sets to each other in that sense. Where neither is natural numbers. If we want to prove something isn't less than or equal, set B has cardinality which is greater than or equal to A, then we don't worry about the surjective part of it. We don't worry about whether we're able to hit everything in B. We just worry about that we're able to really embed A injectively into set B. So if I want to prove something is countable, whether that's infinite or not, then I just need to show that there is an injection from the natural numbers into A. I don't think point 3 really comes up for us, but if you wanted to show that it's strictly less than, then you would need to show that that you can construct an injection, but it's impossible to construct a surjective function. And so I never like defining things based on what they're not. That always sounds a little bit negative. But for an uncountable set, we just define it as any set whose cardinality is not countable. So what we've got so far is we've shown that the cardinality of the natural numbers is equal to the cardinality of the rational numbers and any subset in between them. Sorry. But what we don't know is whether or not that also equals the real numbers, right? So we clearly have an infinite number of real numbers. The question is that infinity the same as the infinities of natural and rational numbers? The answer is no, it's not. Okay, and in fact, the cardinality of the real numbers is strictly greater than the cardinality of natural numbers. And we'll prove that. Any questions? Okay, so I've got the proof here below. This is not something in general that I'm going to ask you to recreate on the final exam, but I do think it's useful to kind of see some of these techniques. This is a really crafty proof technique here to prove this one. And so these are kind of like really seminal, big accomplishments in terms of set theory. So this is that snake lemma is a pretty well-known result, and here is another really powerful result with a nice proof. So, contradiction usually is a good proof technique when we're trying to show that something does not have a certain property. That is oftentimes tricky. So what is a good general comment here is if I want to prove that something is not countable, let me assume it is countable and then come up with some contradiction. Since it would be really hard to prove that there doesn't exist any map which is a bijection, because there's tons of maps that we could consider. So that's why I'm going to do contradiction here. So what that means is, if it's not clear, we're going to assume that the interval from 0 to 1 is countable. And so we're going to prove that we're going to assume that it's countable. And in this case, we know that there's an infinite number of things between 0 and 1. So we're going to assume this is countably infinite. And that's what gives us, therefore, the existence of some bijection from the natural numbers into this interval. That is not a coordinate 0, 1, but that is an open interval from 0 to 1. So if we assume that interval is countably infinite, we have a bijection. So that means for each natural number x, we're getting a unique image a of x, which is in this interval from 0 to 1. And since ax is some real number between 0 and 1, that means we can write it as a decimal. So in this case, ax1 means the first decimal place of real number ax. ax2 is the second decimal digit in the decimal expansion for a2. And so if that notation is confusing, if I had something like okay, that's certainly a real number between 0 and 1. This is just saying we would write this instead as its decimal. And then I would say A31 is 2, A32 is 5, and then all of the rest of them are 0. So each of these terms, a, x, I, some number between 0 and 9. Questions? Yeah, and so if ax is irrational, then its decimal expansion is unique. If ax is rational, then this might be unique, but it might not, right? So for example, I could write a 3 with a bunch of zeros at the end, but let me say like a better illustration of what it means to not write something uniquely is, you might have proven this in a calculus class, that is the number 0.999999 in terms of decimal expansion is the same as the number 1. The limit of this as the digits go to infinity is actually equal to 1. So if the decimal expansion is not unique, then we're just going to assume the expansion are 0 for some position on. So in other words, we would say 0.999 is just 1.0000. We're going to say 0.25 is 0.25 with zeros all the way out. Okay, so I'm trying to come up with a systematic way of saying that we could list all of these things in a way that is in bijective relationship to the natural numbers. And we'll see if we come up with some, we're hoping to come up with some contradiction. So let's just say, again, if this is a countably infinite set, which is our assumption, then we can come up with a list. So I'm going to say, here's my first thing, here's my second thing, here's my third thing, and so on. And so the injective part's not going to be a problem. I can come up with a map from the natural numbers into the interval from 0 to 1, which is injective. But the problem is it's not going to hit everything. So the issue here is going to be the surjectivity part of this. And again, we're doing contradiction here. So we're hoping to prove some contradiction. And our contradiction is going to be, hey, look, this list is going to exclude some values in the interval from 0 to 1. And here is an example of a number that is not going to be in this list. So the claim here is that this number y is going to be excluded from this list. And way I can do that is, well, the first digit of y, the first decimal of y, is 9 minus a1. What we're proving here is that y can't be in this list because it has a different first element than this one. It has a different, maybe this one is the same as this one, but we definitely know that the second decimal is different than the second decimal in 2. And the third decimal is different than the third decimal in 3, and so on. So there's no way that y is going to be in this list because it is going to differ from all of those elements there. This is what we call the diagonalization proof of this. So this proves that the interval from 0 to 1 is uncountable, and it seems reasonable that the real numbers therefore be uncountable, right? Because we can fit 0 to 1 inside of all of the real numbers. So at least what we've shown so far is that the interval from 0 to 1 has more stuff than all of the natural numbers or all of the rational numbers. And that's a pretty crazy thing. There's more numbers in here than there are in there. And what we're going to show next is that there's actually the same stuff between 0 and 1 in terms of real numbers as there are between minus infinity and positive infinity. And that's a pretty crazy thought. Okay. So once we get theorem 6, in case you're kind of curious about this, corollary, if you've heard these terms in mathematics, and theorem, we use these terms slightly different. Like a corollary is something that follows immediately from a theorem. And another word that you may have seen is lemma. And I'll just say, like, lemmas are little small claims that you need to prove along the way to prove a larger theorem. So that's kind of how we use these terms differently. So by looking at corollary 7, hopefully the idea here is I'm going to put some effort into proving theorem 6, and then pretty immediately out of that, we see that since 0, 1 is a subset of all real numbers, then all real numbers are also going to be uncountable. And again, we're hoping to show that A is uncountable. And in situations like this, trying to show something does not satisfy a property, right? These are situations where oftentimes proof by contradiction is good, right? So rather than show that A is uncountable, I'm going to show that if we assume it's countable, we're going to get a contradiction. So one thing to recall here, proof technique, general point, is this is an implication. And actually, P itself is an and statement. So these are kind of what we're calling these different statements. So the implication is, let's assume A and B. U is a subset of A, U is uncountable. Then let's show statement Q is true. And so when we're doing a proof by contradiction for an implication, remember, we are going to assume the hypothesis is true, but the conclusion is false, right? That's the only time that statement would be false. So we're going to assume the reverse. So we're going to suppose A and B are true. U is a subset of A. U is uncountable. And A is countable. And again, like if you're not telling me from the get-go that you're doing proof by contradiction, sometimes it looks weird to just like jump into a proof and be like, why are we supposing A is countable? I'm trying to prove it's uncountable. Telling me that you're doing contradiction makes it much more clear what you're doing. But you can see how all these ideas that we kind of started this semester with, logic statements, right? These are important. And they definitely help give us some structure to these proofs. Okay, so we're going to get some contradictions. Hopefully, we're going to either contradict U is a subset of A, that U is uncountable, or maybe we'll show that U has to be countable, something like this. Okay, so what we do know is that since U is uncountable, it is infinite, since we've already discussed that finite sets are countable. And since U is an infinite thing, which is a subset of A, right, we therefore also know that A is infinite, right? Since everything in U has to be in A, and there's an infinite number of things in U. Right, and we also assumed from the get-go, using our contradiction technique, that A is countable. So we've got A is infinite because U is infinite, and A is countable by our assumption. So A is infinitely countable, right? It's infinite and countable. So we've got contradictions. Anyone see the contradiction? Yeah, so someone just chatted in that you can't have an uncountably infinite thing be a subset of an infinite countable thing. Right, this theorem right here says that U is an infinite set, right, of what we just proved. A is an infinitely countable set, or countably infinite set. So by theorem 2, that's our contradiction, because we assumed that that U was uncountable. And now this corollary, right, that follows pretty quickly from that. Big result there. That took a while to convince people as well that there are different infinities. Pretty crazy. Come back to our kind of list. We've got all of these things are really the same. right? But then these are less than, say, 0, 1, which is equal to the cardinality of R, or any subset of R. Kind of convince yourself that we can think about the complex numbers as like R cross R. And we can build things like that. Maybe I'll kind of leave Theorem 8 as an exercise, but I just want to kind of comment on something that really upsets me when I see people say incorrect things mathematically. So yeah, if anyone has seen or read this book or seen the movie Fault in Our Stars by John Green, very, very sad story. But there's some part in it where one of the characters kind of is giving eulogy, and she says the following stuff. Most of this is incorrect, stuff about infinities. So John, it's not the character's fault, it's the author's fault who made the character say this incorrect stuff. So for example, he's saying, okay, there are an infinite set of numbers between 0 and 1. True, that is correct. There's 0.1, 0.12, 0.112, she gets it, great. That is not true. There are the same amount of infinite things between 0 and 1 and 0 and 2. And between 0 and a million for that matter. So maybe what she should have said is there's an infinite number of integers and then there's an infinite number of real numbers, and that some infinities are bigger than the others. If John Green had consulted me, I would have edited that part of his speech. But yeah, there are different types of infinities. He is correct about that, just he compared infinities that are actually equal to each other when he was trying to make his point about that. So if we're comparing infinities here, just to be very clear, bad example there. There's the same number of stuff. Kind of, I just want to end things here with these different types of infinities. So the natural numbers, these are our countably infinite. Then the power set of n, we can show that that's the same amount of stuff that are in the real numbers. And that's more than what's in the natural numbers. And we denote this with an olive 1. This is like the next type of infinity. And then if I take the power set of the real numbers, which we can think of as the power set of the natural numbers, we get another infinity that we call olive 2, and so on and so on. So there's actually an infinite number of infinities. This is some really beautiful and complicated set theory involved here. But if you're kind of curious about this, this is definitely beyond the scope of this course, but it is in the textbook. There's a nice theorem called the continuum hypothesis, which you might think, how do we know that there's no other infinity between the natural numbers and the real numbers? And this is what's called the continuum hypothesis, is that there's no set A whose cardinality is between the natural numbers and the real numbers. All right, it's early, but you can pop the champagne. We're done with Math 3000, so that's a wrap for that, got some extra time as well. So if anybody has any questions about anything we talked about today or anything you're working on for homework, you're welcome to stick around. The plan for Wednesday is going to be different. I'm sorry, I kind of went through stuff on my own today. We didn't have any breakout rooms, but I think this stuff is quite complicated. So I just kind of wanted to give us a chance to go through it together. But on Wednesday, just gonna kind of talk about the exam a little bit. And then if you have any, it'll be more like an office hours. I mean, if you have some questions, specific or general, bring them with you and we can talk about them on Wednesday, but I'm not gonna be presenting new material on Wednesday. Again, our exam 3 is a week from today, exactly at this time. It's not a final, it's just focused on what we've done since the last exam. And in that sense, you'll have just as much time to complete that as you have the other exams, which is basically an hour and a half, an hour and 50 minutes to work on it, some extra time to wrap up things and then to upload it. And we'll do that the same way. So I haven't added those links yet, but I'll add those links later this week for the exams, and it'll be active on Monday. Okay, so otherwise that's a wrap. So if you do have any questions, feel free to stick around. Otherwise, I'll see you guys on Wednesday.